Hi guys, welcome back to my video. Imagine a world where particles can be in two places at once. This isn't just a science fiction fantasy, it's a fundamental aspect of quantum mechanics. In this bizarre realm, particles like electrons and photons can exist in a state of superposition, where they occupy multiple positions simultaneously. This defies our everyday experiences and challenges our understanding of reality. Where information travels instantly across vast distances, this phenomenon, known as quantum entanglement, suggests that particles can be interconnected in such a way that the state of one particle instantly influences the state of another, no matter how far apart they are. It's as if the universe has a hidden web of connections that transcends space and time, where the act of observing something changes the very nature of what is being observed. This is the essence of the observer effect in quantum mechanics. When we measure a particle's position or momentum, we inevitably disturb its state, introducing an element of uncertainty. This isn't just a technical limitation, it's a fundamental aspect of the quantum world. This is the strange and wonderful world of quantum physics, a realm where the rules of classical physics break down and reality itself becomes a hazy, uncertain landscape. In this subatomic world, particles behave in ways that are completely counterintuitive, leading to a reality that is far more complex and mysterious than we ever imagined. For centuries, physicists believed that the universe operated like a giant clockwork machine, with every event predetermined and predictable. This deterministic view, rooted in classical physics, suggested that if we knew the initial conditions of a system, we could predict its future with absolute certainty. However, the advent of quantum mechanics shattered this notion. Then, in the early 20th century, a series of groundbreaking experiments revealed that, at the subatomic level, the universe behaves in ways that defy common sense and challenge our very understanding of reality. These experiments, conducted by pioneers like Niels Bohr, Werner Heisenberg, and Albert Einstein, uncovered the strange and unpredictable nature of quantum particles. These experiments showed that particles like electrons and photons don't always behave like tiny billiard balls with well-defined positions and trajectories. Instead, they exhibit wave-particle duality, meaning they can act both as particles and as waves, depending on how we observe them. This duality is a cornerstone of quantum mechanics and has profound implications for our understanding of the universe. Instead, they can exist in multiple states at once, a phenomenon known as superposition. In this state, a particle doesn't have a single, definite position or momentum. Instead, it exists in a cloud of probabilities, only taking on a specific value when measured. This concept is beautifully illustrated by the famous thought experiment of Schrödinger's cat, where a cat in a box can be both alive and dead until observed. It's as if a single coin could land on both heads and tails at the same time. This idea is not just a theoretical curiosity. It has practical applications in the emerging field of quantum computing. Quantum computers leverage superposition to perform complex calculations at speeds unimaginable with classical computers, potentially revolutionizing fields like cryptography, materials science, and artificial intelligence. This inherent uncertainty is not simply a limitation of our measurement tools, it is a fundamental property of the quantum world. The Heisenberg uncertainty principle formalizes this idea, stating that we cannot simultaneously know both the position and momentum of a particle with arbitrary precision. This principle has profound implications for our understanding of reality, suggesting that the universe is fundamentally probabilistic rather than deterministic. It means that the future is not preordained, but rather exists as a spectrum of possibilities, constantly in flux until the moment of observation. In this view, reality is not a fixed, unchanging entity, but a dynamic, ever-evolving tapestry of potential outcomes. This perspective challenges our classical notions of cause and effect and opens up new avenues for exploring the nature of existence. This probabilistic nature of reality is one of the most profound and mind-boggling aspects of quantum physics. It forces us to rethink our understanding of the universe and our place within it. As we continue to explore the quantum realm, we may uncover even deeper mysteries and gain new insights into the fundamental nature of reality itself. The journey into the quantum world is just beginning, and it promises to be an adventure filled with wonder, discovery, and endless possibilities. Perhaps the most bizarre and intriguing phenomenon in quantum physics is entanglement. This concept has fascinated scientists and laypeople alike for decades, pushing the boundaries of our understanding of the universe. Entanglement occurs when two particles become linked in such a way that they share the same fate, no matter how far apart they are. This connection is not just theoretical, it has been demonstrated in numerous experiments. Imagine two coins flipped simultaneously, one landing on heads and the other on tails. This is what we would expect in the classical world, where each coin flip is an independent event. However, in the quantum world, two entangled particles are like two coins that are linked together invisibly. If one coin lands on heads, the other must land on tails, regardless of the distance between them. When we observe one coin and find it landed on heads, we instantly know that the other coin must have landed on tails, even if the two coins are light years apart. This defies our everyday experiences and challenges our understanding of reality. This instantaneous connection between entangled particles is what Einstein famously called spooky action at a distance. He was deeply troubled by this phenomenon, as it seemed to contradict the principles of relativity. How is this possible? No one knows for sure. The mystery of entanglement continues to puzzle scientists, leading to various interpretations and theories. It seems to violate the fundamental principle of locality, which states that objects can only be influenced by their immediate surroundings. This principle is a cornerstone of classical physics, making entanglement all the more perplexing. Yet countless experiments have confirmed the reality of entanglement, suggesting that there is a deeper level of connection between particles than we currently understand. These experiments have been conducted with increasing precision, leaving little doubt about the existence of this phenomenon. The implications of entanglement are not just theoretical. Quantum entanglement is being explored for practical applications, such as quantum computing and secure communication. These technologies could revolutionize the way we process information and protect data. Entanglement also raises profound questions about the nature of reality itself. Are particles truly separate entities, or are they part of a larger, interconnected whole? This question touches on the very fabric of the universe and our place within it. As research continues, we may uncover new insights into the nature of entanglement and its implications for our understanding of the cosmos. The journey to unravel this mystery is far from over, and each discovery brings us closer to a deeper understanding of the universe. Scientists around the world are working tirelessly to explore the depths of quantum entanglement. Their efforts are paving the way for new technologies and expanding our knowledge of the quantum realm. As we delve deeper into the quantum world, we're reminded of the vastness and complexity of the universe. Entanglement is just one piece of the puzzle, but it is a piece that challenges us to rethink our understanding of reality. The phenomenon of spooky action at a distance invites us to look beyond the visible and explore the hidden connections that bind the cosmos together. It is a testament to the wonder and mystery that still await us in the realm of quantum physics. Another fundamental mystery of the quantum world is the dual nature of light. This enigma has puzzled scientists for centuries and continues to be a topic of intense research and debate. For centuries, scientists debated whether light was a wave or a stream of particles. This debate dates back to the early days of scientific inquiry, with various theories proposed to explain the nature of light. In the 17th century, Isaac Newton proposed that light was made up of tiny, indivisible particles called corpuscles. Newton's corpuscular theory suggested that these particles traveled in straight lines and could explain the phenomena of reflection and refraction. This theory explained phenomena like the reflection and refraction of light. According to Newton, when light particles encountered a surface, they would bounce off or bend, much like tiny billiard balls. However, in the 19th century, experiments showed that light also exhibits wave-like behavior, such as diffraction and interference. These experiments, conducted by scientists like Thomas Young, demonstrated that light could create patterns of constructive and destructive interference, a hallmark of wave behavior. This led to the development of the wave theory of light, which proposed that light was an electromagnetic wave. James Clerk Maxwell's equations further solidified this theory by describing light as oscillating electric and magnetic fields. The problem is that both theories are correct. Light doesn't fit neatly into one category or the other. Instead, it exhibits properties of both waves and particles depending on the experiment. Light behaves like a wave in some experiments and like a particle in others. For instance, in the double-slit experiment, light creates an interference pattern indicating wave-like behavior. Yet when observed, it appears as discrete particles. This wave-particle duality is not limited to light. It also applies to matter. The concept of wave-particle duality extends to all quantum particles, including electrons, protons, and even larger molecules. Electrons, for example, can exhibit both wave-like and particle-like behavior. When electrons pass through a double-slit apparatus, they create an interference pattern, just like light waves. Yet, they also appear as individual particles when detected. This duality is one of the most profound mysteries of quantum physics. It challenges our classical understanding of the universe and suggests that the quantum world operates under principles that are fundamentally different from our everyday experiences. It suggests that our classical concepts of waves and particles are simply inadequate to describe the true nature of reality at the quantum level. The wave-particle duality forces us to rethink our notions of what constitutes a particle and a wave, and to accept that quantum entities can exhibit both behaviors simultaneously. The strange and counterintuitive laws of quantum mechanics have profound implications for technology, particularly in the field of computing. Traditional computers store information as bits, which can be either a 0 or a 1. Quantum computers, on the other hand, utilize qubits. A qubit can exist in a superposition, representing both 0 and 1 simultaneously. This fundamental difference allows quantum computers to perform calculations at an exponentially faster rate compared to their classical counterparts. Imagine searching through a maze. A classical computer would explore each path one at a time. A quantum computer could explore all paths concurrently, finding the solution far more efficiently. This immense processing power holds the potential to revolutionize fields like medicine, materials, science, and artificial intelligence. Imagine developing life-saving drugs, designing entirely new materials with unprecedented properties, or creating artificial intelligence that surpasses human capabilities. All made possible by the power of quantum computation. Thank you for watching. Video if you like video. Please subscribe channel for more videos.